All right, guys. Last two sections in chapter 5 very closely related to talking about rational functions. So a rational function is just a fraction with a polynomial on top, polynomial on bottom. So it's polynomial fractions is what it is. It's what a rational function is. And depending on how complex they get, things going on. But there's some rules that go along with these. The same rules apply in this section as do next section, and then there's a few other things that happen that they wait and throw in section 5. To me, it's just easier to have it all at the same time and get it all together because they're dependent. The things that happen in section 5 are dependent on what happens in section 4. The things you learn there. So I'm just going to put it all together. We'll go from there. So this is finishing up chapter 5 here today. So with rational functions, if you've got a polynomial on top and a polynomial on the bottom, then you've got a red flag for your domain because you're gonna have x's in the denominator, and that's one of our red flags that happens. So for our domain, if there's an x in the denominator, how do we use that to find our domain? Set what equal to 0? Denominator, yeah. Set the denominator equal to 0. All right. Now, set that equal to 0. That's going to find you the things that x cannot be, your restrictions on the domain. And we're going to get that domain. You're going to do that first before you simplify anything because, you know, it's a fraction, so we got to look to see if it'll simplify, all that fun stuff. So before you simplify, you're finding the domain. Even if something's going to cancel out, you find the domain before you simplify. All right. Then the next step is to simplify the fraction. And if you're going to simplify a fraction that has polynomials in it, then it's going to take factoring. Okay, that's going to be your method for simplifying. You're going to factor the numerator, factor the denominator, and then go from there. So when you go to find that domain by setting the denominator equal to 0, you're better off to use factoring to solve that if possible. Most of the ones you're going to see will factor in some way for that. So factoring is going to be your method for this, and got to remember with polynomials in sections 1, 2, and 3, we dealt with polynomials and we learned how to factor them even if they wouldn't work with grouping or some other method. So we've got those skills still apply here, that you've got to think about it. If it won't factor in a normal way, you got to think about it in that way, and that you can still factor it. All right. So once you've found that, then we get into this thing or these things called asymptotes. Asymptotes are these imaginary boundary lines. ASYMPTOTS. Okay, asymptotes are like these imaginary boundaries that kind of shape the graph. Polynomials, we have, nice little curves and going through like that. With rational functions, you're going to have these asymptotes that are boundaries. And what it does is like the graph of a rational, it may be coming along this way, and there's this asymptote right here that's my right arm. And it'll come up to it, and it'll just start turning that thing, and it'll start getting vertical along with that asymptote if it's a vertical asymptote. Then you have horizontal asymptotes, and we could have what's called oblique asymptotes. When those occur, there are certain scenarios with the rational function that make that happen. And this is the thing, you've got to know these rules for that. So here's how we're going to decide that. Okay. First type of asymptote you're going to look for is a vertical asymptote. It's the easiest ones. Vertical asymptotes are closely related to the domain. Okay, the denominator equal to 0. That's how we found our domain. The difference is when we're finding those asymptotes, we're dealing with the simplified version, okay? So the denominator of the simplified fraction, that's the difference. That your vertical asymptotes a lot of times will be the same equation as what you found for your restrictions on the domain. If you found that x couldn't be 2, then you probably got a vertical asymptote at x equals 2. That there would be this vertical line at x equals 2 that shapes the graph. If there were some simplifying that happens, then you lose. It doesn't match up perfectly with your domain, but it's going to be part of your domain is going to be part of your vertical asymptote. So you're going to kind of kill 2 birds with 1 stone. When you find that domain, you're going to have the factored form. You're going to already have your equations for vertical asymptotes. You've just got to look and see which one gets canceled out, if any of them do. They don't always cancel. Sometimes they do, sometimes they don't. So vertical asymptotes, we're going to look at the denominator of the simplified fraction, set those pieces that are still left equal to 0 and solve. We've already set them equal to 0 and solve when we found the domain. So we'll see that as we do an example that, hey, you're already doing part of this when you find the domain. Okay. The next type of asymptote is horizontal. Horizontal asymptotes. Here's one of the rules that makes those occur. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote we'll abbreviate that HA from here on out. So if I say HA, horizontal asymptote, that's what I mean. So we don't have to write that over and over. That horizontal asymptote, if the degree of the top, the numerator, is less than the degree of the denominator, then our horizontal asymptote is going to be y equals 0. Y equals 0 is a horizontal line. It's right on top of the x-axis. Okay. If the degree of the numerator is smaller, less than the degree of the denominator. Okay. An example of a problem that has that property would be something like this, where you had like x squared plus 9x minus 3 over x cubed plus 1. The degree of the numerator here is 2. The degree of the denominator is 3. So this is smaller than the degree of the top is smaller than the bottom. So we know that this particular rational function has a horizontal asymptote at y equals 0. Just by looking at the degrees. No work involved in that. So knowing that rule gets you one of the situations with the horizontal asymptote. The other situation that there could be a horizontal asymptote in is that if the degrees are the same, if the degree of numerator and denominator are equal, then the HA is y equals, and I'm going to write this fraction a over b. What that means is the coefficients of the degree terms. Another word for that would be leading coefficient for the polynomials. So if we had, here's an example of a problem that has that property. Maybe something like 3x squared plus 5x minus 7 over 4x squared minus 2x plus 13. Okay. Both of them have x squared as the highest power in the numerator and the denominator. So we know that the degrees are equal. So the horizontal asymptote is going to be at the ratio of the leading coefficients, top over bottom, so 3/4. So our horizontal asymptote for this one is y equals 3/4. And you would reduce that fraction if it was like 6/8 or something like that, you reduce. But it's just, you have a dotted, a horizontal line at y equals 3/4, and that would be your horizontal asymptote. Okay. That never happens together, because remember, there's a rule for y equals 0. That's the degree of the top is smaller. If the degrees are the same, then you take the ratio of the leading coefficients. No real work involved so far. The only work we've had to do so far is domain, and that helps us get vertical asymptotes. Horizontal asymptotes are dependent on these two rules. Know them. Okay. Okay. Looking at the degree of numerator and denominator. The other type of asymptote that we can have is what's called an oblique asymptote. Some old school folks like Coach Mack would call it a slant asymptote. When I was in high school, we called it slant. But the new word that they try to use here is oblique. It means it's slanted. We have vertical asymptotes, we have horizontal asymptotes. Oblique asymptotes go at an angle. And they're straight lines. So oblique asymptotes are lines. When do they happen? Here's the rule for oblique asymptotes. If the degree of the numerator is one more than the degree of the denominator, then there is an oblique asymptote defined by long division. Told you it was going to come back up. Also know that the oblique asymptotes are linear, so they have an equation y equals mx plus b. Okay. Oblique asymptotes, slant asymptotes only happen if the degree of the top is one more than the degree of the bottom. So an example of that would be something where we had x cubed plus 27 over x squared plus 9. This is an example of one that has an oblique. We know it has an oblique because the degree of the top is 3, the degree of the bottom is 2. Okay. Would oblique asymptotes and horizontal asymptotes ever occur at the same time? Why not? How do we decide if it even has an oblique or horizontal asymptote? The degrees. None of the rules overlap. Okay? So oblique and horizontal asymptotes. If you have a horizontal asymptote, you don't have an oblique. If you have an oblique, you don't have a horizontal. Okay, they never occur together. So horizontal and oblique asymptotes never, as my little boy says, never ever occur together. He doesn't talk about asymptotes like that. You ask him, do you want a snack? Never ever. It's fun. Yeah, never ever. Okay. But it's code for give me a little Debbie snack or something. He does want snacks. Now, the oldest, no. He doesn't. He never ever wants a snack hardly. So If he does, it's vanilla wafers. That's the only snack we have for him. It's only one he'll eat. All right, so let's look at a few problems and build this stuff up. All right. We'll start with those rules and work with those, and then we'll add in the stuff from section 5. This is just section 4 stuff. All right. So here's our first rational function. F of x equals x squared plus 7x plus 12 over 4x squared minus 1. All right. So this is what we're going to do. We're going to find the domain. We're going to find the horizontal asymptote, if there is one. Or excuse, let's find the verticals first, because that's related to the domain. Vertical asymptotes. We're going to find the horizontal asymptotes. And then if they exist, and we're going to find the obliques if they exist. Okay. So these 4 things are what we're doing right now. All right. So first thing we want to do is find the domain. And to find the domain, we're going to do what? Set the denominator equal to 0. So we got 4x squared minus 1 equals 0. The smart thing to do is factor that to solve it. Don't solve it by square roots. Factor it to solve it. Because you're going to have to factor it anyway to decide if anything simplifies. So that's a difference of squares. What squared is 4x squared? It's 2x. What squared is 1? 1. 2x plus 1, 2x minus 1. We have 2 factors. We set each of those equal to 0. And we get x is equal to negative 1/2. X is equal to positive 1/2. Those are the things x cannot be. We're just going to write the domain in set notation, okay? Instead of doing interval notation in this, because there's a lot to do, you know. So I think set's probably easy enough, you know, easier, especially for this. So x does not equal plus or minus 1/2. That's our domain. Again, set the denominator equal to 0. You want to try to factor it, because we're going to factor everything we can anyway to try and simplify the rational function. So we know that the denominator factors as 2x plus 1 and 2x minus 1. So I want to go ahead and factor the numerator to see if anything will cancel. What's the numerator in factored form? Multiply to be 12, add to be 7, be 3 and 4, right? So it's x plus 3, x plus 4. Does anything cancel out? Do we have matching factors? Remember doing rational expressions in Algebra 1 or Algebra 2, you're looking, you can cancel vertically. So if you got matching pieces on top and bottom, those matching pieces can cancel each other out. They have to be matching completely, though. You can't cancel out this x with part of that 2x. You know, it's got to match perfectly there. If it's addition or subtraction, that's what makes them different. So nothing cancels. What that means is that I've got 2 vertical asymptotes, because nothing canceled out of the bottom. I got 2 factors in the bottom. I got 2 vertical asymptotes. Looking at the simplified. This is simplified. Technically, that's simplified too. We have to factor it to try and see if it will simplify them. Okay. So our vertical asymptotes are going to match these 2 equations. It's going to have equals to instead of not equal to. Okay. So it's x. Our vertical asymptotes are at x equals negative 1/2 and x equals positive 1/2. Those are our 2 vertical asymptotes. And again, that comes from the denominator of the simplified rational function. Okay. Now, since nothing canceled, I can kind of look at my rules from the original problem. Does this have a horizontal asymptote or an oblique asymptote? Why? Degrees are the same, 2 and 2, right? Say it again, Christian. Absolutely. It'd be 1 over 4. The ratio, since they're the same, the rule is it's the ratio of the leading coefficients. There's 1 in front of x squared. There's a 4 in front of x squared. So it's y equals 1 over 4. Horizontal asymptotes will always be y equals some number. Since we have a horizontal asymptote, what's that mean about obliques? Not any. So we're going to write none. Not too bad. All right, let's look at another one. See if we can. Here's our function. X squared plus 7x plus 10 over x cubed minus 25x. And again, we're going to do the same things. We're going to find the domain, the vertical asymptotes, the horizontal asymptotes if they exist, and oblique asymptotes if they exist. Technically, vertical asymptotes, you have to say if they exist too, most of the time, with the ones that you're seeing. Happy birthday. Thanks, sir. Appreciate it. All right, so domain. What do we do? Denominator equal to 0. What now? Factor out an x. There's a GCF of an x. That leaves us x squared minus 25. Will that factor, the x squared minus 25? Yeah, it factors as x plus 5, x minus 5. No, they're not all going to be differences of squares. Be able to recognize those. We all remember the x method pretty good. It's the other stuff that we sometimes forget. So, or that's what I've seen in the past. So how many restricted values am I going to have? Yeah. If it were x to the 4th and x squared here, you would factor out 2 x's. Whatever the greatest number, it's always the smallest set of that variable. So yeah, if it were x squared and x to the 4th, you'd pull out 2 x's out of that. That's right. Okay. So how many restricted values am I getting here? Well, I get x equals 0. That's 1. X equals -5. That's 2. And x equals +5. So this one gets me the x equals 0. This one gets me the -5. This one gets me the +5. You're setting each factor equal to 0. I think we're at a level where you can do that in your head. So x such that x does not equal -5, 0, or 5. That's a pretty long, lengthy sentence in interval notation if you needed to put that in there. So set notation is fine. Okay. Now, so we have the factored form of the denominator. We're going to use that because we're going to simplify. So x minus 5, x plus 5. I did it in a different order there. It doesn't really matter. The numerator then factors as multiply to be 10, add to be 7, 2 and 5. So x plus 2, x plus 5. Do we have any simplifying that happens here? X plus 5 is going to cancel each other out. So that's, here we have one that simplifies a little bit. So x plus 5 cancels x plus 5. So now this is the simplified version. Okay, that's the part we're looking at from here on out. What does that mean about vertical asymptotes? How do we get vertical asymptotes again? Simplified version of the denominator and do what with it? Good. Set it equal to 0 and solve them. So we've only got 2 left here. We got x and x minus 5. So we're going to set those equal to 0. So one of our vertical asymptotes is at x equals 0 because there's nothing to do to solve that. And then if we set x minus 5 equal to 0, we get x equals 5. So we have 2 vertical asymptotes here, one at 0, one at 5. Notice that that's the same values as from our domain, but we lost one of them because we had some simplifying that happens. That's where the difference can happen between domain and vertical asymptotes. If something simplifies, it's going to kind of, you lose one, okay? All right, now, what's the degree of the top? Looking at the simplified version. X plus 2 is the only thing left on top. So what's its degree?
1.
1. What's the degree of the bottom?
1.
2, because we got x times x minus 5. So if you multiply that back out, it'd be x squared. So the degree of the top is 1. The degree of the bottom is 2. What's that mean about horizontal asymptotes? Y equals 0, because the top is what to the bottom? Less than. Doesn't matter how much less. As long as the top is smaller than the bottom, then it's y equals 0. You don't have to do any calculations. Don't even have to find the fraction anywhere. It's just y equals 0. Since we had a horizontal asymptote at y equals 0, what's that mean about obliques? No, you won't have one. They never occur together. Okay. Again, degree of the top was smaller than the degree of the bottom. It doesn't matter by how much. If you had x squared on top and x to the 32nd on the bottom, it's still y equals 0. Okay, that doesn't. How much it's different when the top is smaller doesn't matter. As long as the top is smaller, it's y equals 0. That's the way you want to think about that. Now, last one we're going to do where we're just doing this, and then we'll add the other things in there, which are not that terrible. Example C. Here's our function. F of x is equal to x cubed plus 8 over x squared plus 6x plus 8. Again, we're going to do the same things. We're to find the domain, vertical asymptotes, horizontal asymptotes, or oblique asymptotes. Should be a little more streamlined on our process here. What do we do for domain? Denominator equal to 0. So we're setting x squared plus 6x plus 8 equal to 0. Again, how are we going to try to solve that? Factoring. Is that the only way to solve that? We could do quadratic formula. That would give us the right pieces, but it wouldn't help us simplify the fraction. So that's why we're choosing factoring. Okay, so it factors as x plus 4, x plus 2. Set those equal to 0. You get x cannot be negative 4, x cannot be negative 2. Thank you. And then, so that's our domain. X does not equal negative 4 or negative 2. Again, X method for factoring on that's what I did. Just did it in my head since it was a pretty simple one. So the denominator is that. We have x cubed plus 8 on the top. X plus 2, and then what's the other factor? Because it's a sum of cubes. Remember, sums of cubes factor a certain way. Not quite. There are some sign changes, but it's not quite what you said. You're on the right track. Well, isn't that a polynomial, x plus 8? If we factor it using some of the skills we learned in section 1, 2, and 3, we could graph x cubed plus 8 and see where it crosses the x-axis. It's going to cross at 2. And then we could run 2 through with synthetic division, and we would get what's left. We get the other factor. That's a option. Or memorize that x cubed plus 8 is actually x cubed plus 2 cubed. So that factors is x plus 2, x squared minus 2x plus 4. Now, that's a memorized pattern. That every sum or difference of cubes factors the same way. That whatever's cubed, it's x plus 2, because it's x cubed plus 2 cubed. It's the cubes here. It's the same sign in the middle. Then the leftovers are, okay, I used one x, so there's an x squared. I used one of the 2's, so there's 4 left. That's 2 squared. And then the middle piece is you multiply x and 2 together and then change the sign. That's a memorized pattern. If you don't do it that way, maybe on a scratch piece of paper, you're going, oh, x cubed plus 8 is 1, 0, 0, 8. And I know it crosses the x-axis at 2. So I could run synthetic division for that. 1, 2. Or negative 2, not positive 2. Think. So that's negative 2. So that's negative 2. And then that'd be 4. And that's 4. And that's negative 8. And that's 0. So that means, oh, this is x squared minus 2x plus 4. So that's using the skills we've learned in the last 3 sections. Okay. So that's one way to get it factored. Or memorize the way sums and differences of cubes work. If you graph x cubed plus 8, x to the third plus 8. Where's it crossing the x-axis at? Negative 2. That's where that's coming from. Okay. And then I'm just doing synthetic division to get the other factor out of that. Okay. So that's one way to factor it, or just memorize the sum and the difference of cubes pattern. Well, is there anything that multiplies to be 4 and adds to be negative 2? No. So it won't break down any further. If there was, then you would, but it doesn't. Okay. Now, what simplifies? X plus 2's cancel each other out, right? What's our only vertical asymptote? X equals negative 4. What's the degree of the numerator? Squared, right? And on the denominator? 1. 2 over 1. Be oblique because our degree is 1 more on the top than the bottom. Okay? So that's an oblique asymptote. The way we're going to find oblique asymptote is through long division. So we're going to divide x plus 4 into x squared minus 2x plus 4. Or if you wanted to, you could go back to the original problem and divide them. Yes, ma'am. It canceled out up here. See these factors that canceled? That's why it's not in the vertical asymptotes, because it got canceled out in the simplifying step. Okay, so if it has an oblique, what do we know about horizontals? There aren't any. If it's got an oblique asymptote because the degree of the top is 1 more than the bottom, then we know it has an oblique asymptote, which means it does not have horizontal asymptotes. Okay. Let's do this long division. What times x gives me x squared? X. Distribute. X times x is x squared. X times 4 is 4x. Subtract. That'd be These cancel out. Negative 2 minus 4 be negative 6x plus 4. What times x gets me negative 6x? Negative 6. That'd be negative 6x minus 24. Subtract 4 minus negative 24. Be 4 plus 24 is 28. So that's the remainder. The remainder doesn't matter, guys. Remember, what kind of equation is an oblique asymptote? Linear. Y equals mx plus b. Look at the green part up here. Isn't that mx plus b? That's our oblique asymptote. Nope. You're right. Y equals x minus 6. And that's your oblique asymptote. Okay. What's that look like on a graph? So if we graphed, I'm just going to graph the original problem. X cubed plus 8 divided by x squared plus 6x plus 8. All right. So here we see this kind of curve shape. See how this is kind of getting straight right there? If I graph that oblique asymptote, it's gonna come up through here and look like it's getting close to that line. That's what's gonna happen. I'm gonna graph it so you can see it. X minus 6. This red line coming in there, that's our oblique. Notice how that blue curve it's getting closer to that. If we zoomed out, you'd see it getting even closer to it, and then start lining up with it. It'll never get perfectly straight there, but it's going to get closer and closer and closer. The more you zoom in, there's still a little bit of an angle on it out of that. Okay? And a rational function can cross an oblique asymptote or a horizontal asymptote. It's possible that it crosses it, but it doesn't happen very often. That's one of the things we're going to talk about in section 5, is doing that. All right, so let's look at section 5 real quick. And you can just continue on that page and just say, hey, this is where 5.5 starts. It's still rational functions. We're still doing all of those things. We're doing the domain, simplifying. Then we're getting all those asymptotes. And then we're going to find the intercepts. And then we're going to look for things called holes and crossing horizontal or oblique asymptotes. Okay. So that's what section 5 adds, are those two. Finding intercepts. What kind of intercepts can we have? X intercepts and Y intercepts. X intercepts, when do they happen? X crosses the x-axis. So how do we find that algebraically? Yeah, y equals 0. Set the whole thing equal to 0. F of x equals 0. Solve it. Okay. How do we find y-intercepts? Yeah, find f of 0. Plug a 0 in for x, and that's going to get you the y value. Okay, that's going to get you y-intercept out of that. Okay. All right. Let's get into that. Holes and crossing the obliques and horizontals, we're gonna I think seeing that's the best thing. A hole occurs when something cancels. We've seen some things cancel already. A hole in the graph is going to be coming from those restrictions on the domains that aren't vertical asymptotes, because It's kind of like that example we had earlier where we had an x plus 2 that canceled out. So -2 was a restriction on the domain, but there wasn't a vertical asymptote there. There's an empty spot. It's like an empty circle. We've seen that on some of the graphs that we've seen in the book from chapter 3 on, that there would be a line going and then there'd be this empty circle and then the line would pick back up and keep going. That's what a hole is. It's an empty spot, an X value that doesn't count. It's from the domain, but it's not a vertical asymptote. So it's coming from those canceled factors. That's where a hole comes from. Crossing the obliques or horizontals, that's just going to come from, okay, well, we're going to set the problem equal to that asymptote and see if we get an X value back. If we do, it crossed it. If we don't get an X value back, it didn't cross it. Okay? So let's look at examples. X squared, f of x equals x squared minus 4 over x squared plus 5x minus 14. Again, we're going to do all those things we did in section 4. Domain, vertical asymptotes, horizontal asymptotes, oblique asymptotes, all of those same things. Okay? So to find the domain, denominator equal to 0. That hadn't changed. Nothing is changing here. How does that factor? X plus 7, x minus 2. So that means our domain x cannot be -7 or +2. -7, +2. There's our domain. So that's nice. Gets us our factored form of the denominator, x plus 7, x minus 2. What's the numerator factor as? X plus 2, x minus 2. What cancels here? X minus 2. Okay, so that means the only vertical asymptote we have is x equals -7. Because the only factor that's left is x plus 7. We know that that's going to equal, when we set it equal to 0 and solve, it's going to be x equals -7. Okay? Then we look at the degrees to decide about horizontals and obliques. Horizontal. All right, the degrees are both 1. So what is the horizontal asymptote? Y equals 1. Technically, it's 1 over 1, but yes, that simplifies to be y equals 1. Because the leading coefficient here is 1, the leading coefficient here is 1. So 1 over 1 is 1. So our horizontal asymptote is at y equals 1, and that means that the oblique asymptote is done. Okay. Now, here's where we come to the number 4, number 5. Finding intercepts, holes, and if it crosses. So let's first find the intercepts. Okay. We got X intercepts and we got Y intercepts. Okay. I'm going with the simplified version. X intercepts. What'd y'all say to do to find the X intercepts? So Y equals 0, right? So that means set the problem equal to 0. So we got X plus 2 over X plus 7, and we've set it equal to 0. How do we solve that? Yeah, it's multiplying by X plus 7 to get it out of the denominator. And what's 0 times X plus 7? X plus 2 equals 0. So that means our x-intercept is at -2. So our x-intercept is at -2, 0. That's what we get out of that, okay? So if we were to graph this thing, we'll look at the graph too. We'll see it crossing the x-axis at -2. Okay. What's a shortcut to that? You could look at the graph, but what if it's like crossing at square root of 6? That's hard to see. Instead of setting the whole fraction equal to 0, what part do we end up working with? Just the numerator. The denominator doesn't even matter when it comes to x-intercepts. Okay, so you could just skip this whole step here and just go, oh, the numerator is this, set it equal to 0 and solve. That'll save you 5 seconds out of your life. It really doesn't help much, but it helps a little. Okay, so how do we find y-intercepts again? Set x equal to 0. So we're plugging in 0 for x. So that's 0 plus 2 over 0 plus 7. So that's 2/7. So it's crossing the y-axis at 2/7. So we get x-intercepts, we get y-intercepts out of that. Okay. Sometimes you'll have more than one x-intercept. Very rarely will you have more than one y-intercept. Almost, in fact, never. But now, last thing we want to look at are holes and if it crosses the x or the horizontal asymptote here. So the hole, we had a canceled factor. Okay, that's what causes that. If you've got a canceled factor, you know there's a hole at the x value for that. We need to find the ordered pair for that. That's what we need to do. Okay, we know that x, what's the x value that was in the domain that wasn't a vertical asymptote? The +2, right? That's the part that canceled out. So we know that the x value of the hole is +2. We need to find the y value that goes with that. All we got to do is then plug in 2 for x. Kylie? Okay. So we're just plugging in the x value that was a restriction on the domain that was not a vertical asymptote. And work it out. I'm plugging it into the simplified version. 2 plus 2 is 4. 2 plus 7 is 9. So it's 4/9. There's a hole in this graph at 2 4/9. That means when you graph this, if you were having to draw this by hand, you at 2 4/9, you go to that point and you put an empty circle. And then you would draw the rest of it. We'll graph it on the graphing calculator and I'll show you what it does for the hole. It doesn't show it to you. You just got to know it's there. And I'll show you how you can verify that that's the right place. Okay. Now, does it cross the horizontal asymptote? Cross asymptote. The only way to decide that is instead of having to chase the graph, you could graph the thing and then end up having to zoom out like who knows how many times to decide if this crosses it. Algebraically is the way you want to do that. So if does it cross the asymptote? Well, it's a horizontal asymptote, which was y equals 1, right? We're going to set the simplified version equal to 1 because that's what y is. If I set x plus 2 over x plus 7 equal to 1, that's going to tell me does it cross it. If it's a horizontal asymptote, we're setting it equal to a number. Much easier to do. If it's an oblique asymptotes have equations that are y equals mx plus b, right? So they give you y equals something. Whatever the horizontal or oblique asymptote is, to decide if it crosses it, set the simplified version equal to it. So here, this is the asymptote. The 1 is the horizontal asymptote. No, yeah. Okay, so we're setting the simplified version equal to the asymptote, whatever it is. We're going to solve that. How do we solve that? Yeah, I'm going to do what y'all did to get the x-intercept. I'm going to multiply by x plus 7. It's not as nice here because you got something else to do. So we get x plus 2 equals 1 times x is x. 1 times 7 is 7. And then we try to solve that. If I try to get my like terms together and I subtract x, what happens? I get 2 equals 7, which is no solution. So does it cross the asymptote? No. It does not cross it because we did not get an x value. If it did cross it, you would get x equals something. And that tells you where it crosses. Okay? If the x's cancel out, it doesn't cross it. That's what you get. Yeah. Yes, you would need to find the y value, which you just find by either plugging into the well, we know if it's a horizontal asymptote, we know the y value. If it's an oblique asymptote, you plug that x value into the oblique and give you a number. How that? So yeah, if it does cross it, Kyle asked a great question. If it does cross it, do you find the rest of the ordered pair? Yes, because I want to know where it crosses at. Okay, so that's your evidence. It crosses it at this ordered pair. Okay, let's do one more. Let's do one with an oblique. F of x equals 6x squared plus 9x over 3x minus 2. Make it fairly, not a long drawn out one here. So what do we do first? Domain. Is there any factoring to do in the denominator? No, that's nice. So all we're doing is setting that denominator equal to 0. And what's the x value that's restricted? 2/3. Domain. Again, it's 3x minus 2 equals 0. That gives us that x can't equal 2/3. That x does not equal 2/3. There's our domain. That was easy enough. Now, wasn't any factoring to do on the denominator, but is there some factoring we can do in the numerator? Yeah, we could factor out what? 3x. And that would leave us x plus 2x plus 3. In there. Does anything cancel? No. What's that mean about the holes? There's not any. If nothing cancels, you don't have a hole in the graph. Okay? So that saves you a little work there toward the end. Okay? So nothing canceled. So what does that mean about our vertical asymptotes? Yeah, it's only x equals 2 over 3. Because we had that. And nothing canceled. All right. What about horizontal asymptote? None. Oblique. Why? Yeah, numerator is 1 more than the denominator. If the numerator is 2 more than the denominator, then it's none. Okay, obliques only happen if it's 1 more than the denominator. So how do we find that? We got to do that division. 3x minus 2 into 6x squared plus 9x. I'm going to go ahead and put plus 0 on the end. I don't think it'll matter too much, but might be helpful to have there. Okay, now, what times 3x gives me 6x squared? 2x. Let's say 6x squared minus 4x. Subtract. 9 minus negative 4. All right, got to be smart here. What times 3 gives me 13? Because I need this multiply times 3x to get 13x. What times 3? I know the x is going to be taken care of. What times 3 is going to get me the 13? So 3 times n equals 13. That's what I'm thinking. Fraction. Yeah. 13 over 3. That's the fraction I need. So up here, I'm going to put plus 13 over 3. And yes, that's, a y-intercept on an oblique. That's a fraction. It happens. Okay. It kind of spoiled you in Algebra 1. It made you think everything happened on an integer value. It doesn't. Okay. Most things don't. So distribute that out. There's 13x. Do we need the remainder? No. As long as we know that that's going to get us that part, the remainder doesn't matter because we're only finding the oblique. Is this a slope intercept? We're done then. So you don't have to go through the whole rigmarole of finding the remainder because it doesn't matter. All right. So y equals 2x plus 13 over 3. There's our oblique. Okay. Let's find our intercepts. Let's find our x intercepts. Those are the harder ones. Yeah. Where'd the denominator go? Do you need it? No. Because even if you put it here, you're going to multiply times 0 with it, so it's going to go away anyway. So just the numerator set equal to 0 to get x intercepts. I'm using the factored form because I'm going to have to do that anyway, right? You could. I would just go ahead and just do 3x equals 0 and then 2x plus 3 equals 0. And you're going to divide by 3 at some point, right, Gabby? That's right. It doesn't matter when you do it. So x equals 0, and then x equals negative 3 over 2. We've got 2 x intercepts at 0, 0, and negative 3 over 2. 0. Let's get our y-intercept. Will be 0, 0 because the origin is an x-intercept and a y-intercept. But how do you technically find it? Yeah, plug in a 0 into the function. So 6, 0 squared, 9 times 0 over 3 times 0 minus 2. And yes, you do get 0, and it is at 0, 0. Same as this. So if you get the origin as a x-intercept, that's the y-intercept too. That's a oddity that happens, or nicety. I'm not sure which one you call it. Now, the last thing to do is check the holes and crossing asymptotes. Do we have a hole in this one? Why do we not have a hole? Nothing canceled. If nothing canceled, there's not a hole in the graph. Okay, so it's a continuous graph except for the asymptotes. Does it cross that oblique asymptote that we have? How do you know? Has nothing to do with that. Set the problem equal to the asymptote. So we're setting the function equal to whatever the horizontal or oblique asymptote is. One or the other. Okay. So here we had oblique at 2x plus 13 over 3. How are we going to solve that? Yeah. So that's going to cancel over here. We get 6x squared plus 9x. 3x times 2x is 6x squared. 3x times 13 over 3, 13x. 2 and 2x and -2 is -4x minus 26 over 3. When I simplify that, 6x squared, 13 minus 4 is 9x. Move the 6x squared. Move the 9x. Uh-oh. 0 equals negative 26 over 3. No. No solution. So does it cross the asymptote? No. If there's an x left on these, that's when it crosses. If your variables don't cancel out and there's an x left, that's when it crosses the asymptote. Okay? It doesn't happen a ton, but it does happen every now and then. You've got to just check for it. Like here, the x squared and the x both canceled out. If there was an asymptote that it crossed, then you would still, you might have like 10x minus 9x is 1x, and you'd have a number over here. So you'd get an answer. You get x equals something. That tells you it does cross the asymptote. If you get x equals a number. No. These are canceled out. That's 0 equals negative. Oh, I see. Because they're all canceled out. All right. Okay. Let me find my practice problem set here. All right. So follow the instructions in each section. You got to understand that I'm not going to ask you for everything on every problem on a quiz. It's going to ask for individual parts. So you've got to know what parts you need to do first to get the other parts. So that's kind of how you want to approach working through these problems. So there's 5.4, 5.5 is page 382, 7 through 38. Okay. All right. Work day tomorrow.